Hello and welcome to this new video. We are following the book for this lecture series named Contemporary Abstract Algebra 10th edition, and the author is Joseph A. Gallian. Very good book this is. Okay, now we have studied the theory of chapter number 2, and it is time to start the exercises of chapter number 2. In this video, we will solve first two exercises of chapter 2. Okay, we start with the question 1. And the question 1 is, which of the following binary operations are closed? We know that the closure of binary operation means that a binary operation star is called closed if for every element x and y belongs to the set G implies that x star y also belongs to G. Okay. So the first question is, we have to check that subtraction of positive integer is closed or not. To prove something, we have to prove the general, but to disprove some fact, we just need to give one counter example, and that will be enough. So the answer is the subtraction of positive integer is not closed, because if we take two integers, for example 3 and 8, from the set of integers, then sorry, we have to take the positive integers. So belongs to 1, 2, 3 up to so on. And if we take 3 minus 8, because here binary operation is subtraction, we get minus 5, which does not belongs to this set. So for the positive integer, the subtraction is not closed. Okay, next we move toward the part B. We have to check that division of non-zero integers is closed or not. Let's take a counter example, because this is also not true. For example, we take 3 and 7 belongs to set of integers, then the binary operation is division, which is equal to 3 over 7. This does not belongs to Z. Or if we take 7 divided by 3, which is equal to 7 over 3, this is also not integer, so this does not belong to Z. So the answer is, here we will write the answers. So subtraction of positive integers is not closed. And similarly, we write here that division of non-zero integers is not closed. Okay, because we have applied this binary operation between two integers, and the resultant is not an integer, so this is not closed. Okay, we move toward further. The next question is, we have to check that function composition of polynomial with real coefficient. So this is closed because when we take the composition of two polynomials with real coefficient, we again get a polynomial with real coefficients. So this binary operation is closed. The next is we have to check the multiplication of 2 cross 2 matrices with integral entries. We know that if a matrix A has dimension m cross n and the matrix B has dimension n cross p, the resultant matrix C, which is equal to AB, then the dimension of C will be m cross p. And in our case, we have matrix A, which is 2 cross 2, and matrix B, which is also 2 cross 2. Then, of course, the resultant matrix, if we multiply these two matrices A, B, we get again C will be 2 cross 2. So this shows that this manipulation is closed. Okay, we move toward further. Next binary operation which we have to check is exponentiation of integers. First of all, we will see what does it mean. This binary operation is defined as a star b will be equal to a to raise power b, because this is exponentiation of integers where a, b both are integers. Okay. Now we will check that either it is closed or not. For example, we know that the set of integer is -2, -1, 0, 1, 2, and so on. As I have already told you that to disprove some fact in mathematics, we need just one counter example. So in this case, if we take, for example, a is equal to 3 and b is equal to 2, then a star b, which is equal to 3 star 2, and by the definition, this will be 3 square, which is equal to 9, and that belongs to z. So from this choice of integers, we do not come to any conclusion. We take another option. If we take a to be 3 and b is equal to -2, because -2 also belongs to set of integers, and a and b can be any integers. Now a star b will be equal to 3 star into -2, which is equal to 3 to raise power -2, as we see that the definition of exponentiation of integer is if it is applied between two integers a and b, we get a to raise power b. So this is equal to 1 over 3 square, and which is equal to 1 over 9. And that 1 over 9 does not belong to set of integers. So this binary operation is not closed. We can write that exponentiation of integers is not closed. Okay, we move to exercise number 2. In exercise number 2, we have to check which of the following binary operations are associative. First of all, we will see what is the meaning of associative, as we have already seen that if A, B, and C belongs to some set A, and if these elements, for all elements of A star B, here star is the binary operation, star C is equal to A star B star C, then we say that this binary operation is associative. So here we want to check that either subtraction of integer is associative or not. I'm repeating again, in mathematics, if we want to prove some fact, we have to prove generally, but if we want to disprove some fact, it is enough to just give one counter example. So we take a counter example. If we take three elements, 3, 5 and 7, they are of course integers, and we apply the binary operation between these, and here 3 minus 5 minus 7. We want to check either these two are equal because we know the condition or not. If we solve this, this is equal to minus 2. If we solve the bracket, 3 minus 5 is minus 2 and minus 7. And here 3 minus into minus 2, and this is minus 9, and this is 5. And of course, these are not equal. So the conclusion is the subtraction of integers is not associative. Okay, we move toward further. We have to check that division of non-zero rational number is associative or not. So if we take this binary operation between three rational numbers, that will be equal to a over b, because a division divided by b means a over b divided by c, and that will be a over bc. On the other hand, if we take, we will get a divided by b over c, and that will be a into c over b, because if we convert this division into the integer, we will get the reciprocal. So this will be ac over b. It is clear that it is not necessary that always a over bc will be equal to ac over b. We can also check this by some example. If we take 1 divided by 2, because we have to, and according to these two formulas, at the end we will get 1 by 6 and 3 by 2, and these are not equal. So we can safely say that the conclusion is division of non-zero rational numbers is not associative. Okay, we move toward further. The next is function composition of polynomial with real coefficient. If we take three functions f, g, and h, we see that f of g of h of x is equal to f of g of h, or we can write in the other way that this f of g of h of x can be written as f of g of h of x, and also we can write it as f of g of h of x, and that will be f of g of h of x. So this means that f of g of h is equal to f of g of h, and this shows that it is associative. Means the function composition of polynomial with real coefficient is associative. Okay, now we know that the in general the matrix multiplication is associative So for 2 cross 2 matrices, it is also associative. So for any matrices A, B, and C belongs to 2 cross 2 matrix with integral coefficients, we say that A into BC is equal to AB into C. This means this is also associative. Okay. Now we have to check that exponentiation of integers is associative or not. We consider A star B. We know that exponentiation of integers means when we take A star B, we'll get A to raise power B. Okay. So if we take this A star B star C, it will be, we can see that if we solve the inner bracket, we see that this will be AB star C according to this definition, and then this will be A to raise power B C according to the definition. And if we take this the other side, we will get A star into BC, and when we apply again this binary operation, we will get A to raise power B to raise power C. Now we will see by some particular example, if we take A is equal to 2, B is equal to 2, and C is equal to 3. We have to solve these two sides, what we see. Okay. Then A to raise power BC, which is equal to 2 to raise power 6, because the product of B and C is 6. B is 2 and C is 3, so its product is 6, and this is 64. And we take A to raise power B to raise power C. What we see, 2 to raise power 2 to raise power 3, and that will be 2 to raise power 3 is 8. So here we get 2 to raise power 8, which is equal to 256. And we know that 64 is not equal to 256. So actually, we can see that this is not equal. So A star B star C is not equal to A star B star C. So the conclusion is that exponentiation of integers is not associative. So that's all about this video. If you find this video interesting and helpful, please subscribe the channel and like the video. We will see you in the next video.